Today we're going to look at limits at infinity, or what normally is referred to as horizontal asymptotes. You're probably really familiar with vertical asymptotes. These are the places where the function itself is undefined. The denominator, when it's zero, is causing some sort of a problem. In this one, though, it's totally different. We focus on the end behavior of the function. Where is the function tending to go to whenever x is very, very large? In this case, it's the equation y equals L. To find this, we're actually going to use a calculus concept of the limit. The line y equals L is the horizontal asymptote of the graph of f if the limit as x approaches infinity of that function equals L. So any time you want to find a horizontal asymptote, we look at the limit as x approaches infinity. We need to talk about exactly how you find a limit as x approaches infinity. But first, let's look at some kind of strange things that occur with horizontal asymptotes. They're just slightly different, of course, from vertical asymptotes, but they have one other really different property. For example, let's look at a function that has an asymptote at y equals L again. But this time, the function goes through that asymptote an infinite amount of times. The asymptote is still y equals L. Doesn't matter, again, what's happening inside, just what's happening at the end, or that end behavior. So this is actually okay. Okay, now to some examples. First one, limit is x to infinity of 5 minus 2 over x squared. I'm going to start by actually substituting the infinity symbol in for x. Now, you know infinity squared is just some huge number being squared, so we can simplify that to be 5 minus 2 divided by infinity. But the question is, what does 2 divided by infinity actually equal? Well, this is kind of a hard concept to think about because infinity is really a symbol. It's a concept about a number that's way too large to write out. So instead, let's think about some things that are countable, like 2 over 1,000 and 2 over 10,000, 2 over 1,000,000. Look at the values that it's producing. These numbers keep getting smaller and smaller and smaller. So as the denominator gets very, very large and approaches infinity, it'll actually get as close to zero as we can possibly think of. This is another definition we're going to use. The limit as x approaches infinity of any number over infinity equals 0. It's hard to think about, but that means even numbers that are large, like 1,000,000 divided by infinity, still going to be 0. So to go back to our original example, when I substituted infinity in, 5 minus 2 over infinity, this part goes to 0, and the limit itself is just 5. So y equals 5 happens to be the horizontal asymptote of this function. Let's look at another example. In this one, when I substitute infinity in, I get 2 times infinity minus 1 all over infinity plus 1. So you have to think about concepts now. 2 times infinity minus 1 is still some extremely large number. We can reduce that to infinity. And infinity plus 1 is, again, an extremely large number that just is written as infinity. So what do you think infinity over infinity equals? Probably your first guess is going to be 1, because we know in regular math, whenever you take a number divided by itself, you get the value of 1. The problem is that only works for real numbers, and infinity is not a real number. It's a concept. So that is not 1. In fact, it really doesn't even have an answer. Instead, we refer to this as an indeterminate form. It's the mathematical equivalent of really IDK. You have no idea what the answer is. You don't know if it exists or if it doesn't exist. It just means you got to do a different strategy and a different way to figure out the answer. So that's what we're going to look at next. Here are some guidelines for finding limits at infinity of rational functions. It all has to do with the degree of the numerator and denominator. Somehow you want to write down in your own words and notation these guidelines. It's not an official theorem, but it is going to be useful to you, and you'll need to know these for the exam. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is going to be 0. Here, the word degree refers to the highest exponent. Number 2, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. What do you think would happen up to the asymptote if the limit itself doesn't exist? In this case, there is no asymptote, and a lot of functions simply don't have one. And finally, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is equal to the ratio of the leading coefficients. Leading coefficients is just the fancy math language saying the number in front of the highest power. Doesn't matter where it is, if it's in the very beginning of the expression or the end, as long as it's attached to the highest power. Now we'll go back to that same example we were at before. This time, instead of substituting infinity in, as before, where we got an indeterminate form, I'm going to use these guidelines. In this problem, the value of x, its exponent, is 1 in the numerator, and it's also 1 in the denominator. That means they're equal. I'm going to use the ratio of the leading coefficients. That would refer to the numbers in front. So in this one, the number in front is 2. The number in front and the bottom is 1. So the limit equals 2. Again, that refers to the horizontal asymptote. There's an asymptote at y equals 2. All right, here's 3 more examples. In the first one, the exponent is higher in the denominator. That means the denominator is actually moving faster to infinity than the numerator. And we said whenever that happens, that situation happens, it's going to be 0. No work to show, just a comparison, doing mental math for the result. In the second one, the exponents are the same, so the degrees are the same. I'm going to use the ratio of the leading coefficients, the 2 and the 3. This asymptote and limit is 2/3. And finally, in the last one, the degree is higher in the numerator. That means this limit doesn't exist. And apparently, this particular function does not have a horizontal asymptote. So you can see, if you understand what we just did, you have an assignment to do. This is in your textbook. The numbers are out of order, but I want you to do them that way just so you can work through from easiest to most difficult. Start with number 1 and then 15 to 25 odds, 11, 3, 5, and 8. I expect you to check all of your answers in the back of the book, but remember, you won't have any work to show at all for any of these problems. So all you need is a list of your answers, and then again, check your solutions to make sure that you understand the idea. The only one that won't be back there is 8, and I think you'll be able to work together to figure out what the correct answer is. Okay, good luck.